Hello students, in this class we are going to discuss about public key cryptography and RSA. Uh, First let us know about the private key cryptography. See here the traditional private or secret, we can say it as a private or secret or single key cryptography. It should be whenever if it is a traditional private or secret or single key cryptography, it uses only one key and it is shared by both sender and receiver. Okay, by using only one key, it is going to deal the cryptography concept. So it is shared by both sender and the receiver. So if the key is disclosed and the communications are compromised, we can say it is also a symmetric key. That is, a key is not generated and the communications are not compromised. We can say it as a symmetric key. Suppose the parties are equal, hence it does not protect the sender from the receiver for giving the message and claiming it as by the sender. So if whenever it is a symmetric key, it does not protect the sender from receiver for giving the message and claiming it by the sender. See, if you have seen the public key cryptography concept, probably it is more significant in advance with the 3000 year, more than 3000 years it has been using there, it have been using, but probably more significant in advance in the 3000 year history of the cryptography. How we are going to use these keys are, here we are going to use the two keys, that is a public key and a private key. So that is symmetric and asymmetric. Asymmetric, since the parties are not equal, but it is going to use the clever application of a number theoretic concepts to the function. So the complements is not a it is going to use the clever application of the number theoretic concepts to the function. So the complements rather than the replaces the private key cryptography. So why you are going for the private public key cryptography means, whenever it is a developed address, the two key issues, the key, if it is a key distribution, you have to use the secure communication in general without having to trust a KDC without your key. If it is a digital signature, here we are going to verify a message comes in fact that from the claimed sender. So the public invention due to the Whitefield, Diffie and Martin Hellman at the Stanford University in 1976, we can know earlier in the classified community. So it is developed to address the two key issues, that is the key distribution. We have to secure the communication in general without having to trust a KDC with your key. So if it is a digital signature, we can how to verify a message comes in intact to the from the claimant sender. So the public key invention due to the Whitefield is it is known earlier in the classified community. So if we are going depth into the public key cryptography, the public key is a two key asymmetric cryptography, and it is involves in the two keys, that is a public key which may be known as anybody and can be used to encrypt the messages, so and to verify the signatures. If it is a relatively private key, we can know only to the recipient, use it to the decrypt messages and to sign, that is for the signatures. It is infeasible to determine the private key from the public key, and it is asymmetric because those who encrypt the messages or verify the signatures cannot decrypt the messages or create the signatures. So if it is a public key or asymmetric cryptography, it is going to involve involves the use of two keys, that is a public key which may be known by anybody and can be used to encrypt the messages and verifying the signatures. A relatively private key known only to the recipient, use it to decrypt the messages and sign the signatures. If it is infeasible, it is used to determine the private key from the public key. So it is asymmetric because those who are going to encrypt the messages or to verify the signatures, it can't decrypt the messages or create the signatures. See, this is the concept of the public key cryptography. If you have observed, this is a plain text. Okay, this is the encryption algorithm. Suppose if it is a RSA algorithm, the person who are sending is Bob. Here the person, if you have just for an example, here the person who is sending is Bob. Here the person who is receiving is Alice. Okay, here the Bob's public key ring. See, if it is the public key for this encryption algorithm. Okay, here we are performing the encryption algorithm for this text that we are going to transmit it. Okay, here for this public key, what are the keys we are having here? Suppose these are the, if you have observed Joy, Mike, Alice, Ted, these are the keys that we are going to generate here. By performing this encryption algorithm, we are going to transferring this ciphertext. The text which is transferred, we can say that one as a ciphertext. In the previous classes also we have already discussed about that. After receiving the algorithm by the receiver, here the person who are going to receive her or his name is Alice. So he has to decrypt the text. Okay, for that he has to perform the decryption algorithm. So this is for that he has to perform the key on that. This is the Alice private key. After that he is going to get the plain text output. This is encryption with the public key. Okay, this is an example for encryption with the public key. See, these are the public key crypto systems. This is a source for the message. Here we are going to perform the encryption algorithm. This is the encryption algorithm here. This is for this encryption algorithm, the source is the key pair source. From this we are going to get the key pair source. From this encryption algorithm, we are going to take this decryption algorithm. From this decryption algorithm, again we are going to perform the encryption algorithm more than once. That is twice we are going to perform here. Here this is the decryption algorithm. Here we are going to perform the decryption algorithm twice. This is the destination message here. This is the key pair source. Okay, this is the key pair source. This is the public key crypto systems. This is source and this is destination. That is the message from which we are sending the message. We can see this as a source. From to where the message we are sending, we can say this one as a destination. Okay. See, the public key, for the public key applications, we can classify these public key applications into three categories. That is encryption or decryption. Second one is digital signatures. Third one is key exchange. See, some algorithms are suitable for all the users. Others are specific to one. That is, if it is a RSA algorithm, both encryption and decryption is happen. And for that, we are going to perform digital signature. There the key exchange also happened. If it is a elliptic curve application algorithm, here both encryption and decryption is performed and digital signature is also happened, and there also we are going to perform the key exchange there. And next one, if it is a Diffie-Hellman algorithm, here both encryption and decryption is happened, and there the digital signature is also done there, and again there also key exchange is performed. And if it is a Diffie-Hellman algorithm, there we are not going to perform any encryption or decryption algorithm, and it is a digital signature. There we are not going to perform any digital signature. The only thing that we are going to perform is a key exchange. So if it is a DSS algorithm, there we are going to perform both encryption and decryption. And next one is there we are going to perform some digital signature. And again we are not going to perform any key exchange operation. See, these are the public key requirements. The public key algorithms rely on the two keys, where it is computationally infeasible to find the decryption key. Knowing only algorithm and encryption key, it is computationally easy to encrypt or decrypt messages. When it is relevant, that is encryption or decryption keys, when we know that encryption or decryption key. Again, if it is either, if the two related keys can be used for the encryption, with other we can be used for the decryption also for the same algorithms. These are formidable requirements which only a few algorithms have to be satisfied there. But if it is a public key requirement, the public key algorithms mainly rely on the keys where that is computationally infeasible to find the decryption key. Knowing only the algorithm and the encryption key, it is computationally easy to encrypt or decrypt the messages when the relevant encryption or decryption key is known. Either if the two related keys can be used for encryption with other used for the decryption for some algorithms. These are formidable requirements which only the few algorithms are satisfied there. Okay. So what are the requirements that we have to generate for the public key? Here we need a trapdoor for the one-way function. The one-way function should be the function like y is equal to f of x. It is very easy to perform this type of functions, that is y is equal to f of x. If it is in the form of x is equal to f inverse y, it is infeasible. So a trapdoor is a one-way function which has y is equal to fk of x. It is very easy, and if k and x are known and x is equal to fk inverse y, it is easy, and k and y are known, and x is equal to fk inverse y, it is infeasible if y is known but k is not known. A practical public key scheme depends upon the suitable trapdoor, that is about the one-way function. So if we are using the trapdoor one-way function, then we can say that it is in the form of y is equal to fk of x, that, or if it is y is equal to fk of x, it is easy. That is we can perform the type of functions very easily. Okay, when if k and x are known. Even if x is equal to fk inverse y, that is inverse operation for that, then it is also easy to find out if y and k are known. If y and k are not known, we can say it one as a infeasible. Okay. In practical, a public scheme mainly depends upon the suitable trapdoor, that is about the one-way function. See, if you have observed this security of the public key schemes, like a private key schemes, the brute force exhaustive search attack is always theoretically possible. It is always theoretically possible, but the keys that we are going to use is too large. That is, if we are going to use more than 512 bits, like the private key schemes, suppose we have used about the brute force, we have listened about the brute force algorithm also. If it is a brute force algorithm, sometimes the brute force exhaustive search attack is always theoretically possible, but the keys that we are going to use is too large. Here the security relies, what are the security? It is going to rely on the large enough difference in the difficulty between, that is when it is going to perform the encryption or decryption, and it is very hard. That is, suppose if it is a cryptanalysis problems, then it is very hard. More generally, the hard problem is known, but it is made hard enough to the impractical to break. If you are going to perform the break operation, that is impractical. It requires to use a very large numbers, hence it is slow compared to the private key schemes. When if you are going to perform the private key schemes, it is very slow to compare. Okay. See, this is about the RSA algorithm. RSA algorithm is Rivest, Shamir, and Edelman. These three are the scientists. These are the name of the three scientists. Rivest, Shamir, and Edelman of MIT. In 1977, they have done this algorithm. It is best and widely known used as a public key scheme based upon the exponentiation in a finite. It is field based upon the over integers and a modulo prime. So if it is taking the exponentiation like O of log n cube operations, it is very easy to perform. Here it is going to use the large integers, that is up to 1024 bits. It is going to use here. Here the security, due to the cost of factoring the large numbers, whenever if we are going to perform the factoring large numbers, then it is security due to cost of factoring that large numbers is NB factorization takes O of e power log n log of log n, that is operations to the heart. See how we are going to perform the RSA encryption or decryption. See, to encrypt a particular message M, from the sender, we have to obtain the public key of the recipient, that is P of U is equal to E comma N. It computes C is equal to M power E modulo operation where 0 to 0 less than or equal to M less than or equal to M less than N. To decrypt this ciphertext C for the owner, it uses the private key P or R is equal to D comma N, and it is going to compute M is equal to C power D mod M. We have to note that the message M must be smaller than the modulus N. See how we are going to keep this RSA key setup. Here, each user generates a public or private key pair by. Here, if you are going to selecting the two large primes at random P comma Q. Here we are going to compute their system modules. N is equal to P, Q and phi of N, that is P of 1 into Q of Q, P minus 1 into Q minus 1. Here, if you are selecting at random, the encryption key E, where 1 less than E less than phi of N, GCD of E comma phi of N is equal to 1. Here, if you are going to solve the following equation to find the decryption key D, then E of D minus 1 is equal to modulo of phi of N, and 0 less than D less than or equal to N. Okay. Here, if you are going to publish the public key encryption key, then PU is equal to E comma N. If you are going to keep the private key decryption key, then PR is equal to D comma N. Okay. See, now let us see how this RSA works. Because of Euler's theorem, a power phi of n modulo of n is equal to 1, where GCD of a comma n is equal to 1. In RSA, we are having n is equal to p dot q. Phi of n is equal to p minus 1 into q minus 1. Carefully, if you are going to choose E and D to be inverses, mod phi of n, then hence E dot D is equal to 1 plus K dot phi of n for some K. Okay. Hence C power D is equal to M power E into D is equal to M power 1 plus K into phi of n. That is M power 1 into M power phi of n of K. So M power 1 into 1 power K is equal to M power 1. That is M mod n. See, this is the example for RSA key setup. First of all, we are going to select the primes. P is equal to 17 and Q is equal to 11. Now we are going to calculate the primes. That is n is equal to PQ. That is 17 into 11. That is 187. Now we have to calculate phi of n. That is P minus 1 into Q minus 1. That is 17 minus 1 into 11 minus 1. That is 16 into C. P is equal to 17. If you have taken this value, P is equal to 17, Q is equal to 11, N is equal to PQ. 17 into 11. See why we have taken this multiplication? Why? Because we have taken these two values 17 and 11. So N is equal to PQ. That is 17 into 11. That is 187. So phi of N is equal to P minus 1 into Q minus 1. That is 17 minus 1 into 11 minus 1. That is 16 into 10. That is 160. So we have to select the GCD value, that is E comma 160 is equal to 1. So 1 mod 160 and D less than 160. So the value is D is equal to 23. Since since 23 into 7 is equal to 161. So 10 into 160 plus 1, this is the value that we are going to get. Here the public, if we are going to publish the public key, then P is equal to 7 comma 187. Then we are going to keep this secret private key. PR is equal to 23 comma 187. See, here the sample RSA encryption or decryption is given message M is equal to 88. and encryption is equal to C is equal to 88 power 7 mod 187 is equal to 11. Whenever you are going to perform the decryption, m is equal to 11 power 23 modulus 187, that is 88. So if we are going to choose this exponentiation function, we can use the square and multiplicity of an algorithm. A fast, efficient algorithm for the exponentiation concept is based upon the repeatedly squaring base and multiplying in ones that are needed to compute this result. See, if we are going to look at the binary representation of this exponent, it only takes O of log n to the base to multiplies for the number. Example, 7 power 5 is equal to 7 power 4 into 7 power 1. Just like that we can write. That is 3 into 7. That is equal to 10 modulo 11. Just like that we are going to write. If we have taken this example, 3 power 129 is equal to 3 power 128 into 3 power 1. That is 5 into 3 is equal to 4 modulo 11. That is the exponentiation operation. We can use the square and multiplicity algorithm. It is a fast and efficient algorithm for the exponentiation. Here the concept is based upon the repeatedly squaring base and multiplying in ones that needed to compute the result. Look at the binary representation of the exponent. It only takes the O of log n to the base to multiplying for the number n. See, for C is equal to 0, F is equal to 1. For I is equal to K down to 0, we have to perform the operation do C is equal to 2 into C. F is equal to F into F mod n. If B of I is equal to 1, then C is equal to C plus 1. So, F is equal to F into A mod n. Then we are going to return the value of F. See, this is efficient encryption algorithm. If here the encryption uses the exponentiation to power E. Hence, if E is small, this will be a faster. We can often choose E is equal to 65537, that is 2 power 16 minus 1. And also we can see the choices of E is equal to 3 or E is equal to 17. But if E is too small, if you have taken this example, E is equal to 3, we can attack using the Chinese remainder theorem and 3. The messages with different modulo. If E is fixed, must ensure the GCD of E, phi of n is equal to 1. That is, we can reject any P or Q that is not relatively prime. See, this is efficient decryption. Decryption uses the exponentiation to power the D. This is likely large, insecure if not. So we can use the Chinese remainder theorem to compute the modulus of P and Q separately, then combine to get the desired answer approximately 4 times faster than doing directly. So the only owner of the private key who knows the values of P and Q can use this technique. See, the users of RSA must determine the two primes at random, that is P comma Q. You can select either E or D to compute the others. Let us see how we are going to generate this key. The primes P comma Q must not be easily derived from the modulus n. So we have to, that is modulus of n is equal to P into Q. Means m must be sufficiently large. Typically guess and use the probabilistic test. And the exponents E comma D are the inverses. So use the inverse algorithm to compute the other. So this is the RSA security algorithm. So the possible approaches to attacking the RSA are the brute force key search, and it is infeasible given size of the numbers. So based upon, if it is a mathematical attack based upon the difficulty of computing phi of n, so by factoring the modulus and these are the timing attacks on running of the decryption. So the chosen ciphertext attacks the given properties of the RSA. So now let us see about this factoring problem. If it is a mathematical approach, takes the three forms. Factor n is equal to P dot Q. Hence we can compute that phi of n is equal phi of n, and then D determine, if you are going to determine the phi of n, then directly and compute the D. We can find D directly. So currently believe all the equivalent to the factoring. We have seen the slow improvements over the years. As of as of this May, we can say 20 decimal digits that with the LS. So biggest improvement comes from the improved algorithm. So the CF QS of GSSF to LS. So we can currently assume 10242048 bit RSA is secure. So we can ensure the P comma Q of similar size and matching their constraints. So the number of decimal digits is, suppose if the number of decimal digits is 100, here this is the approximate number of digits. These are this example here. This is the date achieved and this is the years, and this is the algorithm that you are going to use is quadratic save. These are the, this is about how we are going to process the factoring here. See, this is the process in factoring. This is the graph. It is going to gradually increase here from the 10 power 4 to up to 10 power 20. It is crossed. It is the general number, and if it is a special number, it is also increased from up to not when not like general number. The special number is also increased, but when compared with general number, it is slightly decreased. So these are the timing attacks that we are going to face here. So in order to operand size based upon the time taken, the RSA exploits the time taken in the exponentiation. Here these are the counter messages that we are going to get. If you are using the constant exponentiation time, then if you are going to add the random delays, blind values, the blind value should be used in the calculations here in this timing attacks. So what are the chosen ciphertext attacks here? The RSA is a vulnerable to choosing a ciphertext attack. So the attack chooses the ciphertext and gets the decrypted plain text back. So we can choose the ciphertext to exploit the properties of a RSA to provide the info to help the cryptanalyst, and it can counter with the random pad of a plain text or to use the optimal asymmetric encryption padding. We can say it as the optical asymmetric encryption padding. This is how this is a figure related to the optical asymmetric encryption padding. So DB is a data block, MGF is a mask generating function here, EM is encoding message, and H is a hash function here. H is the hash function. M is the message that we are going to encode. P is the encoding parameters here.